I'm not going to talk immediately about the parameterized Bose-Einstein. I'm going to leave that for actually for Wednesday. So the idea of this is kind of break a bit the pace of the last talk about beyond GR, testing beyond GR theories. So it shows kind of topics that I think, at least in a fundamental physics working group, people are interested in. And in particular, Susanna already talked about alternative theories of gravity, how to test them, or at least some particular classes, how to test them with MRIs. On Wednesday, I'm going to continue in this pace of talking about other types of tests of GR, especially in testing them in a parameterized way. And if I hope I will have time, I want to say something also because there was questions about it this morning. I want to say something about going beyond vacuum GR, in particular environmental effects. But now, in this lecture, I'm going to focus on something else. I'm going to focus on something I think is really, really important to do, which is to test what we are seeing, right? Are we really seeing black holes, even with LIGO, but with LISA, I think this will become quite one of the main questions that we will have to make is whether what we are seeing are actually black holes or something else. Okay, so to go there, I took this picture from the book of Kip Thorne. If you've never read this book, I think it's a wonderful book. If you like history, for example, I think, and if you like to know the history of the developments of the field of black hole physics in the 60s and 70s, this is a book. I think I forgot to put the year, but it's around from the 80s. So after this, what people normally call the golden age of black hole physics, which is basically the 60s and 70s, where a lot of what we understand nowadays about black holes was written down. And Kip Thorne gives a very nice account of the developments of this time, a lot of fun facts, etc. So it's a really nice book to read. And I took this picture, these illustrations from the book, which essentially is related to this notion of what we call the Noether theorems. So essentially, in very simple terms, what the Noether theorems tell us is that no matter how you form a black hole, all black holes in the universe look the same, kind of. Or they look roughly the same because they only depend essentially on two parameters. So this is basically an idea of, for example, imagine that you have a star with some magnetic field. It collapses, and what you form is not really a black hole with a magnetic field. It's actually a black hole with nothing. So the magnetic field, if you don't have any matter around that can grab this magnetic field, you will finish with a black hole that is essentially just a spherical black hole, if you want. If you have a cubic star, let's say, you will not end up with a cubic black hole. Your black hole will be spherical at the end of the day, independently of the form of the star. Even if the star was crazy, at a crazy form, you will always end with something that looks like a spherical black hole. And if you had, for example, these are a sort of the same example. If you have a star with a mountain, for example, let's say, or anything with a mountain on top of it, you will not finish with the collapse. Gravitational collapse will not give rise to a black hole with a mountain. It will give rise to, again, a spherical black hole. So this is basically, it's the main idea behind Noether theorems, but black holes are not only interesting because of this fact. There's a lot in them that I think is really fascinating. And so a lot of these perhaps you already know. What perhaps I think we should all have in mind is black holes, essentially they hold the failure of GR, right? Inside a black hole there is essentially a singularity, and we know basically our best theory of gravity is failing there. And this was basically the reason why Penrose got the Nobel Prize, right, 5 years ago, because of the singularity theorems. But the singularities are not the only peculiarity of the black holes. As you know, there's an event horizon that basically tells you there's the region where you don't have access to, and your outside observer cannot have access to the interior of your black hole. There's also something perhaps well, some of you perhaps have heard about it, or the last theoretical, perhaps you never heard about Cauchy horizons. They're not super important because they are always inside the event horizon. So I'm not going to talk anything about that. But in any case, there are peculiarities, especially when you have rotating black holes or charged black holes. There's something else that will be quite important later on, which is a light ray. There is a radius or sphere around the black hole called the the photon sphere, sorry, or in spherical spacetime you can call it actually the light ring or photon sphere because it's actually spherical. For rotating black holes, it's not exactly a sphere; it's actually a shell. But the main idea is that at this point in this light ring, there's an exact. If I send a light ray exactly at that light ring, the light ray will do a circular orbit. So I can see basically the back of my head, right? If my head is sending a light ray from my back, and I'm sitting exactly at the light ring, I could see the back of my head because the light will go around. Another thing that is special about this light ring is that the light ring is actually an unstable circular orbit. So it's the only circular orbit. Well, simplifying things, for example, if you consider a non-rotating black hole, it's an exactly circular orbit. And it's the only circular orbit for light rays, or for, more technically, for null geodesics around the black hole spacetime. And this null geodesic is unstable. What this means essentially is if I don't send the light ray exactly at the light ring, anything that is slightly inside it will fall towards the black hole. Anything that is slightly outside it will go towards infinity. This will become important later. There's also other features that are quite interesting, but I will not discuss them. For example, there's an Negro region if you have a spinning black hole. An Negro region is essentially a region around your black hole where anything is forced to co-rotate with the black hole. No matter how much you try to go in the other way, you will always co-rotate with your black hole in that region. And also quite important for accretion disk physics, for example, there is for massive particles or for things that are not lights, essentially, so anything that has a mass, there is also an innermost stable circular orbit. So basically, this is the last circular orbit in your black hole spacetime where you can have a stable circular orbit. So let's say that was just to, because I know that the audience is quite diverse, so I'm not sure how many of you have heard about these concepts, so I wanted to at least mention them. There is something, so the reason why we do say that no matter how you form your black hole, you always end up with the same object, sort of, is because actually there's uniqueness theorems within GR that tell you that essentially this comes from a series, of course, of works over the years, that tell you essentially that any isolated, and the isolated is important here, stationary, the word stationary is also important, black hole in the Einstein-Maxwell theory, so Einstein-Maxwell is basically your general relativity plus an electromagnetic field, for example, is described by what we call the Kerr-Newman metric, Kerr-Newman family of black holes. And I put here basically the equation that describes the metric that describes this black hole geometry. For those of you that have zero GR background, it doesn't matter really. It doesn't really matter what this is. What is important here, I can write down basically an equation in one slide that describes a black hole. You cannot do that with any other macroscopic object in the universe. That's an essential point about black holes, is that they are actually extremely simple in a mathematical sense. And that's important, especially when we will talk about precision tests or gravity. But anyway, so this formula essentially describes generically a black hole with some mass m, black hole, some spin j, and some black hole charge q in general. Normally we drop this black hole charge because it has been shown that essentially black hole charge is irrelevant in astrophysics. You can think, quite easily if you have something that with as a charge, for example, it will quickly attract opposite charge particles and neutralize. So this process in general will occur in a very fast time. There's some works actually computing the time scale that you will need to discharge whatever charge black hole you will have, and these are extremely fast times. So that's why we normally neglect the black hole charge. So going back to the Noether theorems, what these theorems in the mathematical, these theorems, what is important that you notice is that these are mathematical statements. So these are mathematical theorems that in general, the typical statement is something of the sort. If I have an isolated stationary black hole in GR plus some matter field, some type of matter that satisfies certain conditions, these conditions normally is conditions such as the matter is stationary, the matter satisfies, for example, some energy condition. Then there's a bunch. This is not one theorem. It's actually a family of theorems that tell you that the Kerr family, if you neglect the black hole charge, so Kerr will be a black hole with only spin and mass, is the most general family, even if you have matter in your equations. Suzanne already said that, but there's nothing. This is very special, but we know exactly how to break this theorem. So all these theorems come with certain assumptions, and there's many examples of what we call airy black holes, and they exist, for example, in beyond GR, as Suzanne already said. But even in GR, we know exactly cases of airy black holes in GR. I'm not going to talk about them, but most of them are more mathematical curiosities, if you want. And the reason is because if you consider only matter fields, so only type particles within the standard model of particle physics, the Noether theorems that we know seem too old. That said, and the reason why I have this slide is because I want to emphasize, although we always call, and you see it in papers, testing the Noether theorem, it's a bit wrong to say that we are testing the Noether theorem. Noether theorem is a mathematical fact, right? I mean, you write a theorem with some assumptions and you prove your theorem mathematically. What we're actually trying to test is what some people have called, for example, the Kerr or the Noether hypothesis. And these hypotheses are basically telling you that the Kerr geometry, so black holes with only mass and spin, described by the metric that I showed before when that Q is equal to 0, basically can describe all isolated black holes in the universe. This is not a small statement, right? I'm saying that there's millions and millions of black holes in the universe, and I can describe all of them with the simple equation I wrote down in the previous slide. So it seems, I have a theory, it works, but the fact that I'm claiming that, it's a big claim, right? There's perhaps nothing else in physics that is such a big statement as this one. And in fact, Sander Zecker, back in '75, in a lecture that he gave, he wrote this statement that I think is quite basically describes the message I'm trying to pass, which is how stunning was that there is an exact representation, mathematical exact representation of untold numbers of black holes that populate the universe. Again, there's no other macroscopic object that you can describe so easily. So given this big claim that we are making, essentially, right, how can you test this? So this is what I'm talking about. When I talk about testing the Noether theorem, that's exactly what I'm talking about, or exactly how to test this statement that we are making, that I can describe all black holes in the universe using a very simple equation, so the Kerr metric. So there, basically, here comes basically your binary black hole gravitational wave, and I'm going to kind of schematically describe exactly in a waveform like this, how can you test the statement that your black holes in your binary are described by the Kerr metric. And if you look at it, essentially you can describe, as you've probably have heard already in the waveform modeling lectures, or probably you already have heard these many times in the past, you can describe your waveform in basically three parts: an early in spiral part, what I'm calling late in spiral, and then the merger ring down part, right? And if I want to look at this waveform and try to get information about what are the objects in the waveform, essentially the early in spiral part doesn't really carry any information about the objects. So you can think about when the two black holes are quite far apart, or two whatever objects are quite far apart, right? I cannot really, I mean, the scales are such that I cannot really see the structure of these objects in the waveform. So the objects essentially behave as they were point masses. So the only thing I can ask when I'm looking at the value early in spiral is questions such as, is this orbital decay, so is the waveform evolving in such a way that is consistent with GR? But this is not really a statement about the object, it's just a statement about the theory that describes how this waveform evolves, and in particular the orbit decays. Next Wednesday, if I have time, I'm going to also mention at least, and something else you can ask in the early in spiral is whether these objects are moving in vacuum. This is especially important in this early in spiral part because it modifies the way the waveform, the orbits decay. If you want to understand more about the objects, you really need to look more into the late in spiral and ring down. So in the late in spiral, you start having finite size effects, or effects from the fact that you don't have really point masses, but these are objects with some finite size. And you also have tidal effects, as you probably know. The most famous case is neutron stars, for example. But you could think about objects that are not black holes, that are mimicking black holes, that will also be tidally deformed. And so you can start asking, are these objects, through using the waveform, are these objects black holes or something else, or in the late in spiral? And then if you go to the ring down, which essentially, as you know, is basically tells you that after you merge, this object that you formed will relax on a given time scale and seems to settle down to some final state. And you can, looking at it, you can ask whether this is ringing like you expect it for a black hole. So I'm going to look into these two bits in this lecture. I'm looking first in the late in spiral. And to do that, I'm going to first go back to Newtonian physics, because I think perhaps some of you have already heard about that. And try to describe, if you look at an object, right, you look at the gravitational potential of an object, how can you, from the gravitational potential, know the structure of this object? So know exactly what this object is made of. So a way that you can do that is through, for example, if you solve your Poisson equation, so your Poisson equation describing basically all the gravitational field of some objects with density rho, how this gravitational potential looks like in the exterior of your object. Outside your object, you can basically describe your gravitational field in what is called basically a multipolar expansion, where the idea is that you're expanding your gravitational field outside the object in powers of 1/r, essentially, and well, essentially in a spherical harmonic basis. It so happens that every L in your spherical harmonic basis decays as a higher power in L. So, for example, let's say the typical example is something that is just a point, right? A point with some mass m. This will be basically just something that is essentially spherically symmetric. So the only term here will be the 0, mode of your spherical harmonic, which is just a constant, and this formula will give you the typical m/r of a Newtonian potential of an object. However, if you have something more complicated, like, for example, this is literally the representation of the gravitational field of the Earth, represented to what is called the multiple moments, where essentially these numbers that you can compute to these integrals. And essentially, they tell you how far away from spherical symmetry this object is, essentially, right? So anything that is above L equals 0 will tell you that this will have a dipole moment, then a quadrupole moment, etc. And the more deformed your object is, the more, for example, the more small scales you have in your gravitational field, the higher the L numbers that you'll have. So this is not, I mean, you do also this in electromagnetism, in case some of you remember. So essentially what I was saying, essentially what is written here, if you have a spherically symmetric body, you only have this first term, so that's basically the mass of the object, and any other multiple moment will be 0. For an axisymmetric body, so meaning something that is symmetric over some axis, for example, basically all multiple moments for which m is different than 0 also are 0. So if you want the m number tells you is related to the symmetry over some given axis. And if you have, for example, an axisymmetric and equatorially symmetric body, essentially all the cases for which m, actually there's a typo here, so this should, no, this is correct. Besides this fact, you have also the fact that all the cases for which L is an odd number, these multiple moments will vanish. Another thing to note, just for completeness, is that the L equal 1 term is actually, you can always make it to vanish by choosing the origin of your body to be the center of mass. Okay, so this is Newtonian physics. There's a generalization of this to GR. I'm not going to go into detail. It's mathematically a bit complex. But there is a generalization of this multiplying expansion in GR that was developed first by Gerock and Nansen using a specific formulation, and then Kip Thorne in the 1980 he formulated this in terms of all your metric looks like asymptotically, so very far from your object. And essentially, so this is easier to, this multiplier expansion in GR is normally easier to describe in Kip Thorne's formulation. So in Kip Thorne's formulation, essentially, if you have a stationary asymptotically flat spacetime, any stationary asymptotically flat spacetime can be described by through a set of basically relativistic mass multiple moments that basically this LMM at the generalization of the multiple moments that appear in the Newtonian limit. But you also have another type of multiple moments that are called current multiple moments that are unique to relativity. There's not really a Newtonian limit of these current multiple moments, which basically in Kip Thorne's formulation, they can be read off from your metric as you take your distance from the body to very large values, essentially. So for example, the GTT component, so the TT component of your metric will have information on basically these mass multiple moments, while the cross GTI are basically the components, the cross terms with the spatial part of the metric, where you can read off these what are called these current multiple moments. And specifically, so the reason why I'm telling you all of this is because in Kerr, so for a generically spinning black hole, which the Kerr metric is axisymmetric and equatorially symmetric. So there's the only non-vanishing, so there's a bunch of multiple moments that are 0 just because of this fact. In particular, all the m different than 0 are exactly equal to 0 for Kerr because it's axisymmetric. And because it's equatorially symmetric, there's also a bunch of L's of multiple moments for given L's that are also exactly 0. In particular, all the L's here that are odd will be 0 for the mass multiple moments, while all the L's that are even for these current multiple moments are exactly 0 for Kerr. Not only that, because Kerr only depends on two parameters, so the mass and the spin, all the multiple moments, these M and L's, can be described only in terms of the mass and the spin of the black hole. And in particular, they satisfy this relation. So you don't need to memorize this, but the point here is that all these multiple moments, they only depend on the mass of your body and the spin of the body. And in particular, notice, for example, the mass. The M00 is essentially the mass, and the S1 here. So this S10 is essentially related to the spin. It's essentially the spin of the black hole. So you can think about these current multiple moments being something related to the spin. Okay, that's it. So essentially, what this tells you is if there's a way that I can measure these quantities, these multiple moments, there's a way that I can test whether my metric satisfies those relations, for example, for a Kerr black hole. So there was so in the 90s by I don't remember what the F stands for, but by what normally is called the Ryan theorem, that tells us that essentially this multipolar structure of your body is essentially imprinted in the gravitational waveform in a very specific way if you have a binary system. So if you think about the post-Newtonian expansion and you write down your waveform in this case in the frequency domain with some amplitude and phase, your phase of your waveform, you can write it in terms of a point particle contribution, so all the PN expansion that don't depend on the multiple moments, plus some contribution that comes from that are related to the multiples of your body. So if you can measure this contribution, in principle, you could measure the multiple moments, and from these multiple moments, you can try to reconstruct your metric. Specifically for MRIs, which is where MRIs are ideal because in the case of MRIs, actually when I measure these, I'm really measuring the multiple moments of my central black hole, right? Because I can think about the small body just as a small perturbation of my big black hole. So my big black hole is essentially very closely something that is exactly Kerr plus some small perturbations. So if I can measure the gravitational waves from an MRI, I can in principle reconstruct the multiple moments of my central supermassive black hole, which is very well in principle, if it's a black hole within GR, it should be very well described by Kerr, by the Kerr metric. So these have been mostly looked into the MRI case, but there's work also for non-MRIs, but normally MRIs are much better for this test. And if I write down this piece in a post-Newtonian way, I wrote all of these just to show you that all the multiple moments are actually imprinted in here. But this is the work by Ryan, where I essentially show that the leading order contributions due to these multiple moments. So these are only the leading order for each ML and SL. There's additional terms that are not written down here that, for example, they have like cross terms between ML and SL that are sub-leading to these ones. And these are also just assuming axis symmetry and equatorially symmetric spacetime. If you break these assumptions, things will become much more complicated, and there's also been work on this subject. But what is important here to notice is these mass multiple moments. So they enter at I'm calling relative LPN order, just to say it's relative to the leading order point particle term, essentially in GR. And essentially can read off from here. So this is let's say the velocity of your binary. For some reason, someone decided that a v to the squared is a 1pn term. So here, because you have a v to the 2l, that's a LPN term relative to this leading order term. And while the current multiple moments, they enter at L plus 1/2 PN order. For example, the spin, which is S1, the first term that it contributes to your PN waveform will be at 1.5 PN order. So in particular, it means that to leading order, right? So to leading order, you have the mass of your black hole. Then at 1.5 PN, you have the spin. So this will be the usual stuff. But then also at 2 PN, right? So the M2, at 2 PN, you have essentially the quadrupole. And now if you think about these relations for the Kerr metric, right? So if I'm able to measure the spin, the mass, if this is a Kerr black hole, I should be able to know all the multiple moments of my system, right? So if I measure then another multiple moment, let's say the quadrupole, which is the next leading order term, I can basically check whether this relation is correct, right? Because, so I will imagine I am able to measure the mass, I'm able to measure the spin. Then in principle, if I measure these terms, so in this case, the n equals 0, which is the quadrupole, no, sorry, the n equal 1, sorry. which is the quadruple, I'm able to check this relation for n equal 1, for example. I'm able to check whether this is correct. Yes?
Just to make sure it's a mass spin of the... Just to make sure it's a massive spin of the final black hole, or it's the...
Like yeah, sorry. Yeah, no. So these, here I'm talking specifically just because in this particular example, I'm talking specifically in an memory where there's a mass. This is the mass of the big black hole.
Okay.
So this M here, I'm always talking about the mass of the big black hole.
Okay.
Actually, if you do a more generic mass ratio system, so more equal mass, let's say, what you always measure is actually is a combination of the multiple moments from the two objects. So actually, in that case, it's a bit harder also to constrain because of that, because it's always a combination of the two multiple moments that you actually can measure. So M is also good in that respect because you're really measuring multiple moments of one of these black holes. Okay, so another question. Oh, yeah, there's.
So to use this formalism, you kind of are using that we are in an asymptotically flat space, but cosmologically speaking, we are not.
Yeah.
Does this somehow complicate this, or is it basically just a mathematical footnote?
Yeah.
That
This at the end is just a mathematics, because there's a separation of skills between, let's say, the cosmological horizon, if you want. So your cosmological constant is a very small number. So any effect due to the cosmological constant is basically very far from your objects, which means that when I say this is defined for asymptotically flat black holes, I'm essentially we do that for everything, right? We always consider asymptotically flat, basically because things are so the effect of the cosmological constant is so far from your system. I mean, the scales are so different. Then effectively, if I consider sufficiently large distance from your system, I'm approximately in an asymptotically flat spacetime, and I'm still sufficiently far from the effect of the cosmological constant. So you can do that because there's this separation of scales between cosmological constant and your system that is much smaller than the scale of let's say, the universe, if you want. So, I mean, we do that for everything. I mean, when you compute a waveform, for example, we are assuming I can extract my waveform at what we call null infinity. That's only valid if I'm actually in a asymptotically flat spacetime. So everything we compute assumes asymptotically flat, even though we don't live in an asymptotically flat. But here, that's a more mathematical statement. In practice, is really what I call my infinity, something that is far enough from my system. Okay, very quickly. So this is something that many people have looked at, whether you can actually do this test where you, beyond measuring the mass and spin, that in general you can do very well, where you can measure, for example, the quadrupole moment. And with MRIs in particular, you will be able, again, everything I will say, you will be able to do that with the caveat that reality will be much harder, as you all know. But in principle, in an ideal scenario, the prospects is that with MRIs in LISA, with a typical MRI, you should be able to constrain these quadrupole moments with respect to the Kerr quadrupole moment within a factor of 10 to the minus 5. But this shows this example. This is actually from a paper from Stas. And by doing that, you will be able to check this relation for the quadrupole moment, and that will be a way to check whether the quadrupole moment is actually consistent with Kerr. So that's exactly what we mean by doing a test of the Minoret theorem, right? I'm testing whether my metric, in principle, only depends on 2 parameters. Of course, to do that exactly, I will need to compute all multiple moments, right? But that's technically an impossible thing to do because the higher the multiple moments, the higher NPN they enter, and so the harder and harder they become to measure. Actually, I'm not sure if with MRIs you are able to measure beyond the quadrupole moment. Perhaps, actually, I'm not sure about that. But in principle, you could actually at least measure the quadrupole moment. But so this is not really the only thing that happens in a binary system. It's not only measuring the multiple moments, and in particular the multiple moments, that's something I want to emphasize. Multiple moments are not telling you anything, for example, about whether this is really a black hole. So, and when I say whether this is a black hole, whether there's an horizon, right? Because what defines a black hole is actually the existence of an horizon. The only thing I'm doing with multiple moments is measuring whether my metric far from the object looks like a curve metric. That's not the same thing as saying there's an horizon. So I want to talk about some other effects that appear. Some of them might tell you something about at least quantifying the evidence for an horizon that are related to tidal effects, essentially. So you know that if you have two bodies, there will be also other effects related to tides. Essentially, in the waveform, you also have information about how the objects respond to the gravitational field of the other objects. And there are essentially two, let's say, quantities that quantify this response to an external gravitational field that are essentially what we call tidal love numbers, and also something else called tidal heating. So tidal love numbers are essentially, so this is something that comes also from both these quantities, both these tidal effects are things that come from Newtonian concepts. So tidal love numbers, you can think about some tidally perturbed object due to some external, some external satellite that is far. For example, this will be the Earth, and there's a moon here, for example, that is tidally deforming the Earth. And if you write down the gravitational potential of this tidally deformed body, like in the exterior of the body, essentially, and if you consider initially your body was spherically symmetric, so essentially this first term is just the gravitational potential in the absence of your external body. While now, if at leading order, for example, I consider that your tidal field has a quadrupolar form, that's the leading term if you consider an external body, for example, the moon, like the effect of the moon on the Earth, the leading order term is what is basically something that looks like a quadrupole, so it's basically this term here. So this modifies your gravitational potential that you measure here. So there's an external tidal field, but also modifies, there's an extra term that appears that basically tells you how the body is responding to this tidal field. And essentially this response is proportional to the initial tidal field that you're imposing on your body. And there's a constant here that is exactly what we call the tidal love number. And this tidal love number essentially depends on the structure of your object. So whether you deform something more or less depends on what the object is made of, and everything is encoded in this tidal love number. So this is specifically the leading, so the quadrupole tidal love number is like the main one, but the ones that, for example, are used to, that LIGO, Vero uses, for example, in measurements of binary stars. But there's, of course, an infinite set of tidal love numbers because, you can have also the external tidal potential is an infinite set of multiples. So there's a quadrupolar tidal love number, an octupolar tidal love number, et cetera, et cetera. But the leading one, the one that you normally see in the literature, is typically this one that appears here. So there's also a theory where you can generalize this to GR. What is important here is that the tidal love number are exactly zero for curved black holes in GR. And the GR part is important because you can break the fact that tidal love number are exactly zero if you go beyond GR. But also if your object is not a black hole, it will have a non-zero tidal love number, like binary stars, for example. Of course, LISA will not detect binary stars, but it will detect, let's say, for example, supermassive black holes. But, I mean, we have no idea if those are actually black holes, right? They could be something else. If we make no assumption, and I think we should not make any assumptions because at the end we are doing science, so it's about observation. It's not about really the maths. We should take into account that the fact that if we want to actually test if this is black holes, this is another property that black holes satisfy, and we can try to measure things. We can try to actually measure whether the tidal love numbers are compatible with zero. In particular, if you consider MRIs, so again, an MRI where you have a small body orbiting some massive body of mass m, and if this massive body is not a black hole, then this object will have a non-zero tidal of number, and this will appear in the phase of your gravitational wave, at least in the PN expansion, at 5 PN essentially. Like, I mean, the 5 PN is also what this is a very generic statement that the leading order tidal of number appears at 5 PN. But what is important, if you consider actually an extreme mass ratio in spiral, where m here, the mass of the big black hole is much larger than the mass of the small body, there's actually, this is proportional to this q, which is a very large number for m. So this effect, if your central object is not a black hole but something else, this effect could be actually quite large. So I'm not going to go into details into these plots, but the main idea, so this is something that, of course, there's been work and looking into whether you could measure these. And in particular, so these are the tidal of numbers of some exotic objects that are not black holes, so wormholes, something called gravastars, which are sort of black hole mimickers where you don't really have an horizon, but it will be something that forms a surface close to the horizon. These normally motivated by the information on the black hole information paradox. So if you don't form an horizon, for example, you could solve this paradox. And so people have come up with crazy ideas about ways to solve this, and one of them is gravastars. Don't ask me too much about it. If you take an agnostic approach at least, and you look into what LISA ideally could be able to constrain, which are basically these numbers here. So this k 0.02, this k is basically the tidal of number. So this is a prospect of LISA constraining this. It will be at the level of 10 to the minus 2. So this is showing essentially the same thing, but in a more careful analysis. So you don't need really to care about these plots. What is important is that this line here is essentially the constraints that LIGO could, in principle, put on a tidal of number of the central object in the memory. And in particular, if you look at these numbers, so this 10 to the minus 2, this is 5 orders of magnitude better than what LIGO does with LIGO, Virgo, and Kaga do with binary neutron stars. So it's really telling you, if I measure an memory, if I'm able to actually measure this tidal of number, I'm able to tell you, in principle, that this is something that almost doesn't deform in some sense. Because the tidal of number will be, if you measure something that is consistent with 0, you could constrain it to be very, very small. Okay, any questions about this? Yes.
Just for my own understanding, we can only do this for MREs because for similar mass systems, you basically violate stationarity, right?
So you can also do it for more generic equal mass binaries. I mean, you do it with neutron stars actually. Again, in MREs, it's a bit different when you're measuring in MREs compared to equal mass binaries. It's kind of the same idea as multiples. First, because what you actually measure is always a combination of the tidal of numbers of both objects and not one single one. So for MREs, you are really proving the central object here, not really the binary. And there's also this feature that makes it actually much better than equal mass, that this scales with the mass rate, with the inverse of the mass ratio, which means that this term in the phase for an MRE is actually a very large term compared to more equal mass. That said, about your point on the isolation, I can actually do it because I'm always considering a post-Newtonian expansion, where essentially I'm expanding things in post-Newtonian, where it's point particles, and then I start adding small effects like multiple moments on top of it. But I think things are a bit more complicated when you're considering equal mass, right? Because these tidal effects are something that occur almost at the end of Turing spiral, where it's actually more or less also where the PN expansion starts breaking. So you also have to be careful about whether your post-Newtonian expansion is valid there.
Yeah, I was thinking specifically of the merger phase, like we have to go from 2 blobs to 1 blob, so at some point there has to be some deformability.
That's why, for example, for binary neutron stars, I mean, everything is compared also with numerical waveforms, right? So, I mean, MREs in this respect are a bit better because, I mean, you can describe almost everything with perturbation theory, at least black hole perturbation theory, until almost actually until the merger.
Yeah.
So yeah. Okay. Going forward, the last effect I wanted to talk about, because this is really an effect that is related to the existence of an horizon. The last effect I wanted to talk about in the spiral before the merger is this effect of tidal heating. So tidal heating is something that occurs in any binary system, essentially. So it's actually the reason why the moon is synchronized with the Earth. Like you're always seeing the same face of the moon towards you, and also the Earth is spinning down because of tidal heating effects. And tidal heating is essentially related to the fact that if you're deforming your object due to the tides, right? And there's friction, right? There's friction that created because of the movement of your object, because your object is being deformed, and there's friction in the interior of your object that kind of induces a torque in your object, and this is called, and slows down your object, and this is called tidal heating. For black holes, you can think about, there's something that we call tidal heating that is kind of analogous to that, which is the fact that you can write down, for example, the way, in the adiabatic sense at least, I think Susanna already talked about this. If you consider all your orbit decays over time, basically your orbit decays over time essentially because you're emitting gravitational waves. You're emitting gravitational waves towards infinity, but you're also emitting gravitational waves that are absorbed at the horizon of your black hole. This term here, essentially, which is gravitational waves being absorbed by your black hole, is typically called tidal heating also for black hole, because it has exactly an analogous effect, of what tidal heating is for example, in the Earth-Moon system. What is special about black holes is black holes are essentially, you can think about them in a sort of perfect absorbers. So anything that falls in is absorbed, nothing is reflected. And so, for example, if you had a black hole, this term here, which is essentially parameterized in a very simple way, whether your object is absorbing everything or not, is exactly zero in the black hole case. So you can try to parameterize any deviation from that by putting this parameter R, which is a sort of effective reflectivity, that essentially, if it was exactly equal to 1, for example, if this quantity is exactly to 1, it reflects the fact that you have no term here, so everything is there's no absorption at the horizon. So this is a very simple way to parameterize these, and this is really something that is proving whether you have an horizon or not, right? So it's telling you whether something is really just a pure absorber, like an horizon, or not. Yeah.
Am I correctly understanding? Okay. That anything that is reflected back goes back into the orbit's energy because your flux at infinity stays the same?
It doesn't stay exactly the same, actually. Actually, in this work by Elisa, Martin van der Mint, and Paul Pani, there is some small deviation actually in the infinity flux, if you consider something like that. It is smaller than actually these effects. So there's more than actually just deviation in these parts. Yes.
Sorry if this is a digression. I was just wondering, in what way how is it meaningful? But what does that first term actually mean? dEdt to the infinity. Sorry. So this is meant to mean. I should have put like GW here. So this is meant to be power in gravitational waves that goes towards infinity. Infinity, like far away from the object, and this is power in gravitational waves that is being absorbed by your, in this case, your black hole or your whatever object it is. I see. Okay.
I forgot to put the GW here to be clear. Okay. So this is an example. For example, what will happen if you have something like that, something that actually doesn't absorb all the radiation that comes in. So this is the example between the case. So this R equals 0. It will be basically the black hole case, and this case will be something that something that is very close to the black hole case and something that actually reflects half of the radiation that comes in. And this is something for an emery that has some eccentricity 0.8. This chi is basically the spin, so 0.9 is not super important. This is the H plus polarization as a function of time for something that started, well, it started at 0, and we consider that at 0 you had something that starts going towards the black hole and starts exactly at the same point. As you evolve your orbit, these effects of tidal heating are essentially small in general, but if you consider again an emery, and that's why I mean emeries are special in all senses because they can measure extremely small effects. And if you consider the case of an emery, for example, as you spiral in after 2 months, after you started your spiral, after 2 months in this case, and I think this was a 10 to the 5 solar mass black hole, something like that, mass ratio 10 to the -4, I think. After 2 months, you don't see a big difference between these two curves. So the case where you have a black hole, a binary black hole, and a case where you have something that is very, very close to a black hole, but is not exactly a black hole, you don't see a big difference. But in this curve, which is something that's really, you're almost not absorbing anything at the horizon, well, in this case, there's no horizon, there will be horizon, you see a big difference between these waveforms. So these are really dephased because part of the energy that should have been absorbed is not being absorbed. And essentially, the waveforms, the evolution, or if you want, the evolutionary of your system is quite different between these cases, and that leads to these large dephasings. And of course, if you go to larger, if you wait even more time, you start seeing also a deviation between these two cases. So this is something that people have looked at, but honestly, it needs to be really looked at in more detail. But in principle, with very rough calculations, you can, at least based on mismatch calculation, you can tell apart between waveforms for which these R squared, so this effective reflectivity, is as small as 10 to the -5. Yeah. So you could, in principle, tell whether something is very, very close to being a black hole.
So just wonder if this is GR or beyond GR.
That's a good question. So one thing that is important here is that in GR, at least as far as we know, everything that you consider that collapses forms a black hole, and unless you consider something exotic, you will form a black hole. So there's no known exotic matter that forms something that will be extremely close to a black hole, but not being exactly a black hole. Normally, to consider these effects of something that is not exactly a black hole but is almost a black hole, you need to consider, for example, quantum gravity effect that will avoid the formation of an horizon. I have to say, of course, that all of this is very hypothetical because, well, quantum gravity, if you look at any paper on quantum gravity, I hope no one here is working on it, there's very few calculations, if you want my opinion. And so it's really, normally, I want to solve a problem. I know there's problems with black holes, like the information paradox, the singularity problems, etc. So let's say I can avoid the collapse through some non-local effects or whatever, and you will form something that is not exactly a black hole, but it has to be something that is very close to a black hole because you do observations, and so far everything looks like being in a black hole, right? That said, I mean, from an observational point of view, that's theoretical, of course, and we should at least quantify what is the evidence that we have that we are seeing a black hole. And in my opinion, that's one way to do it is to these several tests, right? Is to say how close to a black hole what I'm seeing actually is. Because another point that is important is that you cannot really tell if something is a black hole by definition of what is a black hole, right? So because a black hole is something with an horizon, and by definition, I cannot see that there's an horizon because nothing from the horizon can come to me, right? So the only way that I know is a black hole is if I enter in a black hole, and this person will never be able to tell me they enter the black hole. So by definition, you cannot tell something is a black hole. You can tell if something is very, very close to being a black hole. So from this point of view, that's what exactly these tests are trying to do. Is that clear? Yes.
Okay. So does the waveform with the tidal heating Like, can it be mimicked by just a waveform without tidal heating and slightly different parameters?
That's a good question, and that's why I wrote here rough estimate based on mismatch calculations, because something follows that we should do is actually do parameter estimation, checking correlations, degeneracies, etc. Because honestly, I think that will be a problem. In some case, at least when you have something that is for which the reflectivity of the black hole case again is when the reflectivity is exactly equal to 0. When the reflectivity is probably not very far from 0, I think there will be large correlations between just mimicking something with slightly different masses, spins, etc. I believe, but that's still to be done, that if you have something that is tidal heating is nearly non-present or very different from the black hole case, the waveforms will look so different that it's very hard to mimic it. That's my expectation. It might be wrong, but that's my expectation. I cannot say 100% that this is true.
Yes, it's because the blue curve and the orange curve.
Especially, I mean, these claims that I'm saying is basically, if you look at this green curve, it looks very different from the others. These two curves look very similar. So that's basically the claim comes from this. Okay, no other questions here. If there's no other question, I'm going to pass to the ring down part. Okay. So this is for what I called here more ISPAL tests, so tests that are related really to not really the final object that you're forming, but before forming the final object. So something else that you can do is to study the final object that you form, for example, in a more equal mass ratio case, and ask the question whether this thing is ringing like what you would expect. So you've already had, I believe, some lecture where you talked about this. I'm going to go a bit quickly onto the first part of actually how you do that. But I just wanted to remind you at least of some basic facts. That the way you can describe this phase, essentially you can think about this phase as some object, right, that is slightly perturbed away from your final, for example, Kerr black hole. So I'm going to show you the case of Schwarzschild just because it's simpler. The equation is simpler. You can do also things in Kerr, as you've heard. But for example, if you consider Schwarzschild, where things are very simple, the way you normally will do it, you start with your Einstein field equations in vacuum because these are black holes, so there's no matter. And you consider, so this is basically Einstein's equations in vacuum. You can write them in this form. And you consider, for example, your Schwarzschild black metric plus some small perturbation that describe essentially that ringing pattern. If you do that, and you can do that with pen and paper, it takes some work, but you can try to do it almost with pen and paper. You can arrive essentially at two equations. This is in Schwarzschild again, so it's in the case where there's no spin, which basically there's two equations essentially because there's 2 degrees of freedom, right? So there's two polarization gravitational waves. Here, so in this context, they are normally called polar and axial. They are related to how this perturbation transform under parity transformations. And these equations always take essentially this form. They have some, what here is essentially an effective potential, but this looks basically like a wave equation with some potential. You can do something similar as you've heard in Kerr. You arrive at something that is called the Tucholsky equation. The reason why I didn't write it here is because in Kerr, actually, the approach is not exactly this one. Normally, what you're actually perturbing is something called the Weyl scalars. If you want is, instead of perturbing the metric directly, you perturb the curvature, so what is called the Weyl, quantities that are related to the Weyl tensor, which is related to curvature. And the reason is essentially because to arrive at an equation for which you can separate angular variables and radial variables, this approach doesn't work for Kerr. At least no one has found a way to do that directly from metric perturbations. Anyway, this is just an aside. Now, I don't know how much you went into this, but I wrote it anyway just to clarify actually what you're looking at. So what you're looking at is, again, something like this wave equation. Now, this wave equation for example, in a Schwarzschild geometry, on a Kerr geometry, because it's stationary, and that part is important, you can actually find solutions that have this form that only depend on this radius. This radius is something related to the radius. Is a coordinate that is written in such a way that your event horizon is at minus infinity, while at plus infinity you are basically far from your black hole, and basically your domain of your equation becomes from something from minus infinity to plus infinity. So it's a convenient radial coordinate. It's not super important. What is important is more looking at these potentials, or the potential of your wave equation, that for a black hole basically looks like this. So essentially, so this peak here, you can actually relate it to what I talked about before, which is the light ring. So the peak occurs roughly at the position of the light, of what I call the light ring. Actually, in the limit of very high frequencies, this is exactly located at the light ring. And essentially, you can think about that in a way that, for example, so if you this is a way, so these for generic frequencies, for example, gravitational waves, electromagnetic waves, they satisfy some equation like that, satisfies a wave equation. In the very high frequency limit, they are basically following geodesics of your space-time. And in particular, they are affected by the light ring, which is a concept that actually only, when we talk about light ring, we're talking about something, we're talking about geodesics. But geodesics in your space-time are only actually valid when you consider something that looks like a point particle. Waves are not point particles, right? They have a finite width because they have, I mean, they are finite wavelengths, right? They don't propagate on a single geodesic. Anyway, so because you have this potential, what is essential about this potential is that this is essentially like a scattering potential. For those of you that have a theoretical background, you're probably looking at things that are similar in quantum mechanics. And in particular, you can find solutions for which your waves at infinity look like outgoing waves, and at the horizon look like ingoing waves. And so if you try to solve your field equation, so your wave equation, sorry, with boundary conditions in this way, there will be specific boundary conditions that will satisfy these conditions. Specific solutions and with specific frequencies that will satisfy these conditions that you can compute through various methods. And in particular, so they are discrete and depend on three numbers. So overtone number, this just some number that's basically because there's an infinite set of solutions. And these L and M, you've already seen them. They are related to the angular separation, to the angular part of your equation. If you want to do this calculation, actually there's a lot of material available online. In particular, if you go to this new center of gravity group, they have a bunch of mathematical notebooks where you can do these calculations. Also, actually deriving the perturbation equations I was writing down. There's some notebooks that can be used for that. And also the black hole perturbation theory toolkit as a bunch of, as some codes to do these calculations. So then if you go and download these codes and do the computation yourself, what you'll find is basically, again, there's, for given mass and spin, there's an infinite set of modes that depend, again, on three numbers, L, M, and N. In particular, I'm showing, for example, the frequency of these modes, and these show you essentially the damping time of these modes. Well, here written in terms, I forgot, it's here. Here, just because in this paper they wrote in terms of what they call the, I don't remember the Q factor. I don't remember what's the name of this Q factor, but there's a name. But it's related. You can invert it to get the damping time from these plots. And in particular, what is important here is that these curves, so these different curves here, are related to the fact that when you go to zero spin, actually all the M modes are degenerated with each other. This is related to basically in the zero spin limit, your black hole is exactly spherically symmetric. And so it doesn't depend on M. When you include some spin, your metric is not exactly spherically symmetric. It's actually like more a spheroid. And so you start having dependence on M and different modes with different m, they kind of split. So the spin kind of split different m's. If you do a calculation of the typical frequencies related to the what is normally called the fundamental mode, so the less damped mode, the mode that has the larger damping time, the typical numbers for LISA, for example, would be for a 10 to the 6 solar mass black hole, it's around the 10 minus 2 Earth, so you can make computations roughly where your waveform will fall by basically plugging numbers in these formulas. And in particular, for example, look, this is so these are 10 to the 6. This is 1 million solar mass black hole that relaxes in 50 seconds. I mean, these are crazy, crazy numbers. I mean, you're forming 1 million solar masses, and this thing goes like, essentially, if you want, this is not really ringing. It's really something that suddenly stops, like in 50 seconds it stops. And if you put numbers in LIGO, right, this is millisecond. So you're forming something with tens of solar masses, and in milliseconds it relaxes to a final state. So it's an incredible statement. When you start thinking about the numbers, these things are really incredible. And after these calculations, you can build a waveform essentially for, so you already seen that. You can build a waveform for your ring down that typically looks like this. So you already seen this, so I'm just writing down again. But I want to emphasize that this is really just part of actually is there. There's more to it than just these simple damped sinusoids. For example, there's non-linearities, and especially when the closer you are to merger, non-linearities might start becoming important. People are looking into these. At late times, there's actually something called tails. That also can become important in some cases, and you can ask questions whether environmental effects can actually impact this. But this is another question. All that said, so what exactly is the ring down? So normally when you hear talk about this, the picture is typical. You have a black hole that rings and then settles down, and there's this picture. Oh, it's actually something that comes from the fact that you have an horizon that settles down. So it's important that you differentiate actually the existence of an horizon and having a ring down. The ring down has nothing to do with having an horizon. So the picture that you should be thinking about, and that's actually, if you go back to the sketching potential, there was that peak at the light ring, right? And it's exactly because of that peak that you can have this mode, so that it's that scattering, the form of that sketching potential, and the fact that you have a peak at the light ring that leads to quasi-null modes. And in a very heuristic approach, and actually you can make this more precise in the high frequency limits, you can actually link the ring down with the modes or with waves that basically circle around the light ring. So if you think something like, for example, something emitting a pulse like here, with some gravitational wave emitting here, the ring down is essentially related, so the frequency of the ring down is essentially related to the frequency of these light rings, so how long it takes to go around these light ring, and the damping times are actually related to how fast, or better, how unstable this light ring is. To put in other ways, because this light ring is unstable, as I was saying, if you send a signal in this light ring, you will not stay exactly in the light ring because the light ring is unstable. So essentially, unless you shoot exactly at the light ring, this wave eventually will go away, and it will go away in a typical time scale, and that time scale is related to the damping time. Okay, I have to go a bit faster, but. So all that said, that was a revision. I think probably you've heard about that in the waveform part, but I thought it was important to re-emphasize parts of it. All of these then can be used also to test the NORA theorems. To basically, I think the first person that actually spoke about this possibility was that Weiler in a paper in 1980, where he put it in a very nice way, measuring these frequencies. Comparing with measuring what is called the 21 centimeter line of the hadronen. So by measuring these frequencies, you can learn about the object that you're detecting. That's why it's called spectroscopy. If you want to read more, there's actually a very nice review. I think some of you were involved. I wasn't, but I know that some of you were involved in this. If you want to read a 250-page review, you can find it here. There's a lot of material in there. It's the most recent review on this subject. Okay, but what exactly does it mean to do this spectroscopy? So again, in Kerr and in GR, these frequency and damping times only depend on mass and spin, right? So imagine that I have something, so I did that because, well, when I did this plot, I was thinking about Einstein telescope, cosmic explorer, so the masses are more typical of ground-based detectors, but you can rescale all of these to LIGO if you want with larger masses, but the idea is the same. So you have your black hole, for example, sitting here, for example, your black hole has a roughly 70 solar masses, spin 0.7. And imagine I do a measurement of the first frequency of the 2-2 mode. So if I do a measurement of this 2-2 mode and I plot it in the mass spin diagram and with some errors, this was in this case for something like GW150914 for Einstein telescope. But anyway, the idea is the same for all detectors. What you get is something like that. So you cannot really, because there's only one frequency that you're measuring here, of course you cannot really measure, there's a degeneracy, complete degeneracy between mass and spin. So the measurement, your frequency will fall something in this band for a given frequency that you measure. Now, imagine that you measure a damping time, right? So because now you have frequency, damping time of your, at least the least damped mode, which is the 220 mode. You can do another band here of your damping time, right? And ideally, in the ideal scenario, it will fall exactly if you're in GR, and assuming there's no other problems in the measurements. I know this is more complicated, and in reality, things are more complicated. I know Chantal has work that shows exactly that it's more complicated than this. But ideally, it will fall exactly somewhere where your black hole is, right, in the mass spin diagram. And now, because you have two quantities, and this only depends on two parameters. If you're in Kerr and GR, this already tells you everything about them. You can already say what is the mass and what is the spin of your black holes through these measurements, right? So now, because if this only depends on two parameters, whatever other measurements you do, for example, imagine that you measure the frequency of an additional mode, in this case, the frequency of the 2-3 mode. If you are in GR, this should fall, this band for the additional mode should fall exactly where the other modes are. If it wasn't GR and there was some deviation, you could expect this to kind of deviate a bit. So this is the idea of spectroscopy. I know the word is very complicated for me. Anyway, so with LVK, the idea is that idea is the idea behind this test, but it's not exactly the way it's done, right? So the way it's done is normally you do some you measure, you see some event. So this is this very a large SNR event that was recently observed by the LVK, and you do a measurements of your frequency and damping time of your final the signal in the ring down. And for example, in this event, they measured frequencies and damping times. For example, for one mode that, in principle, you cannot actually know which modes you're actually measuring. Right? You have your waveform, which is just the sum of damped sinusoids. So the most you can do is, if you know, because you detect the signal not only in the ring down, but detect it since the inspal, right? You can have an idea where the damping, the quantities of your final black hole should fall. So these quantities here, these very small contours here, are basically what you will predict for the damping times and frequencies, given what you know from your inspal, well, from your IMR measurement, basically. So then, if you do a test with the ring down with only damped sinusoids, you can measure frequency and damping time. So that's what they did here, for example, and they measure these contours here, which are related, which they can associate with the 220 mode, because it falls right where you would expect the 220 mode. They also see something that seems like related to the 221 mode, so the first overtone. Actually, there's one analysis, I'm not going to talk in detail about this, but also seems to see for indications of the 440 mode. You can also plot these in the final spin and final mass diagram, and the fact that everything seems to, so the IMR result seems to fall inside all these bands seems to indicate there's no deviations from GR, essentially. So this is with LVK. So with LVK, you're not really measuring a lot of modes right now, but things will become really, so of course this is about LISA, and with LISA things will become much more rich, but also more complicated. Essentially because if you, with LISA, you might be able to measure way more, just really a lot of modes, essentially. So this shows you essentially the horizon, so it shows you the distance in, well, here in redshift, or the luminosity distance, at which you can see different modes. In this case, for a given mass ratio, non-spinning binary black holes, but you can do these plots for other systems, of course. But the main idea is that with LISA, you can see, for example, in principle, well, I know there's been some updates to this work, but the main idea is that you can see, for example, very large modes. So these are 2-2 mode, 2-1 modes, 5-1 mode, etc., at very, very large redshifts, right? What this means essentially that in principle you can do these tests of measuring many modes. You can do these tests with the measurement of many modes, and that of course will in principle give you better tests of the Neuer theorem. But also it means that because you can see many modes, it does make the analysis more complicated, right? Because you do need to include a lot of modes to avoid biased measurements in general. Okay, I think I started a little bit later, so I'm gonna, because, sorry, but I'm almost finished, but I wanted to say, of course, so this is just this kind of a null test, right? These measurements of the modes and then checking whether they are consistent with GR, right? So now, what does actually this tell us about beyond GR? Well, in principle, you can at first guess that there's a deviation from GR if you see that your measurements are not compatible. When you do these Neuer tests, they are not compatible with GR. But then the other difficulty is to actually do predictions in beyond GR theories and try to see what they tell us about the ring-down modes. And the naive expectation, this is actually what has been used in a lot of works, is that if you add additional parameters, so instead of just having mass and spin, now you have, I don't know, the Einstein-Gauss-Bonnet theory that, Einstein-Scalar-Gauss-Bonnet theory that Susanna was talking about, where there's an additional parameter, in this case, an additional complete constant. You could expect your modes to deviate from the GR ones through some small deviation that now depends on your additional parameters. This is true that will happen for some modes, but actually there's a bit more physics in the ring down than that in general. For example, something that this parameterization doesn't capture, and something that I forgot, I wanted to say it, but I forgot, is that you might remember that I talked about two types of wave equations. So I talked about polar and axial. And the reason why at the end I only showed one set of quasi-normal modes is because even though there's 2 degrees of freedom for your gravitational wave, there's actually only in GR, only one set of quasi-normal modes. So actually, for example, in the non-spinning case, this polar and axial perturbations, they predict exactly the same spectrum. So we say they are isospectral. Essentially, despite the fact that they satisfy a slightly different equation, they predict exactly the same spectrum. That's not true when you include beyond GR effects. Go ahead. Yes.
So just on this, so
yeah.
Are you saying that the 2 modes? Yeah, sorry, can you explain
yeah.
again?
So well, the easier way to think is that you have 2 degrees of freedom, right? So you 2 polarization, if you want, and each one will satisfy some wave equation and will have some spectrum associated to it. It just happened that in GR you have exactly the same frequencies for both. So when you measure things, you actually don't see like 2 sets of quasi-normal modes. You see one, because there's only one set of, even though you have 2 degrees of freedom, right, in your waveform, there's only one set of quasi-normal modes in your.
But you're not killing
in
1 degree of freedom, right? They're just the same. They're just a copy of one another.
But like for example, in GR there's H plus and H cross, right? Mm-hmm. So it's not exactly H plus and H cross that when you do perturbation theory, that you're actually computing, but there's 2 degrees of freedom. So if you want 2 wave equations, even though these equations are different, they do. When you do that computation on quasi-normal modes, their spectrum, so the frequency and damping times, are exactly the same. Once you break GR, that stops to be true, actually. So actually, this is what this plot is showing for a particular theory. So it's one of the examples that Susanna talked about, where so this plot shows you the real part of the frequency, so the frequency of your ring down, as a function of the coupling constants of this theory. So 0 means GR. So in GR, for example, this for some given spin of the black hole. In GR, for example, for the L, so the L equal 2 mode, M equal, I think that's also the M equal 2, I believe. Your frequency has there's only actually one number here for the L equal 2, there's one for the L equal 3, and there's only these 2 points, actually. Once you break GR to this coupling constant, the larger you make it, you start having 2 sets of modes, for example. Each one related to one particular degree of freedom of your gravitational sector. So this is about the isospectrality breaking, but there's also, for example, in these additional theories, you also have other degrees of freedom. So you have what Susanna talked about, the scalar field. And so there's actually modes related to the fact that you have an additional field. Not only do you have the gravitational perturbations, but you also have the scalar field. So there's actually much more modes in your data than just something simple as this. Of course, one thing is to have all these modes, another thing is the impact that these have in the waveform. You might expect that, for example, the scalar field might be suppressed, and you might expect that, for example, the polar side might be more excited than the axial case, but this is actually, might depend on the theory, and to know this for sure requires doing numerical simulations. And in Beyond GR, in some theories, there's some numerical simulation, but they are quite in the early stages, if you want, and they are quite difficult. So the answer exactly which mode content you will have in some given Beyond GR theories is not really a completely answered question. Okay, I have really to move very fast just to say that the LIGO Virgo already do this kind of test where they essentially you take your GR ring down and you add some small deviation. So you might have some, if you've read the paper on the GW15, well, not 15, the latest ISNR event, you might have seen this plot that shows deviations from the 220 modes, the frequency and damping time. This particular test actually uses, what they do is they use a full IMR waveform and they just add small deviations in the ring down. So that's why actually you can disentangle between this term and this term, because this term is roughly measured due to the inspal. So the inspal tells you what is the mass and the spin of your final black hole. That gives you already a good constraint on this, and then you can measure this deviation in the ring down. And these constraints are basically, you should interpret them this way. With LVK, using a similar analysis, there's also been some work in trying to understand the constraints that you can have. I just wanted to emphasize 2 things without going into details of these plots. You can, well, again, you can measure a lot of these modes, so these 2, 2, 3, 3, 4, 4, 5, 5, unlike what the LVK does. But also the constraints are, yeah, 10 to the minus 3, for example, for some, these constraints for different binary systems with different total masses, different spins, and different mass ratios. In some cases, you can get errors that are around 10 to the minus 3, which are 2 orders, roughly, order of magnitude better than what LDK is doing. Yes.
Yes, and just going back to the previous slide, I was just wondering that
No.
Oh, no. I mean, this is can you? No, sorry. So the one
sorry,
before, the one. Yeah, this one. This is exciting. No, I mean, what's this blue curve? Can you comment?
Well,
it seems like
exciting
there's a big
depends
deviation.
on your perspective. The blue curve is just telling you, this is basically, the blue curve is just telling you that with these events, the deviations from GR and the ring down is at the order of, at most, let's say 10%, a bit less than 10%, I think. the exciting, that's the part I wanted to emphasize actually with this plot and this plot actually. When you do this test in this way, you're not saying much in my opinion. You're just saying this seems to be GR within some relative error. But if you want to say something deeper, you actually have to compute ring down in some theory, compute what this theory predicts, and transform these constraints on different modes and say exactly what this means for the constraints on that particular theory. For example, I can tell you that if you take these measurements in these different modes, you apply it in Lisa, and you apply it to, let's say, the Einstein-Dilaton-Gauss-Bonnet theory that Susanna talked about in the morning, the constraints are not very exciting. The constraints are better with Lisa, with LIGO than with Lisa, even though Lisa seems to do better in terms of these deviations. The reason is because, so these are just the absolute deviation with respect to the GR in this fashion, right? But this will depend in a non-trivial way, in the mass, in the spin, in the additional parameters of your theory, and depending on how it depends on it, it might lead to a nice constraint or to basically a constraint that is not that interesting. So it really depends on the theory. You see what I mean? Or
not quite, but maybe I can ask after.
That's true for any type of test you do. So especially when you do it in this way, you have to. These numbers don't mean much, right? In the sense that they are just telling you something with respect to GR. But when you want to say something more fundamental, you actually have to say what does a specific theory predict, right? And transform that to that specific theory. And the fact that you see 10 to the minus 3 or in LDK 10 to the 10 to the minus 1, something like that, doesn't necessarily mean that it leads to a very, very strong constraint on a given extra parameter in your theory. For example, again, in this, well, I'm always giving the same example, but in the Einstein-Gauss-Bonnet theory, there's already constraints from the inspiral, from dipole emission, that in general is much better, is much stronger than the constraints due to the ring down. Okay, I think I'm not gonna say, well, I just wanted to put this slide. I have actually some extra slide. I might put it in the next lecture just to not bother you in going over time. I just wanted to emphasize, so again, when you're measuring the ring down, you have to be careful about saying that these prove that what I'm saying is a black hole. Because the ring down has nothing to do with the horizon. It has all to do with the light ring, as I was saying, but not really, it's not related to the event horizon. So measuring something that looks like a curl-like ring down doesn't necessarily mean that that you're measuring that what you're seeing is a black hole, or is not the same thing. That's what I want to emphasize. I might show the plots about the other subject in the next lecture because I think I'm slightly already over time. So,
just maybe a last question on the subject of the ring down. If it has nothing to do with the event horizon, I'm curious. What about the neutron star events?
Well, in the neutron star events that you've measured, you actually didn't measure really the merger parts. You measure mostly the inspiral part. Mm-hmm. In the future, you might measure the merger and what you could call the ring down. In neutron star, things can be a bit more complicated, just because you have matter.
But it does have a ring down.
It does have something that looks like. So actually, I'm going to show you this plot because at the end I wanted to show you in the next lecture, but I'll show you it here anyway. It does look very different from a curved black hole in general, from a black hole case, just because the star is not very, very compact. For example, the final neutron star that you merge, if you form another neutron star, for example, at the end of your neutron star merger, neutron stars that you are actually forming don't have a light ring. So the oscillations that you're actually seeing, they are related mostly to the matter, to the modes related to the matter sector. They're not really related to the space-time, to the geometry modes. So they are a bit different, actually. And that's why it looks very different from a black hole. So that's actually the point of this that I wanted to make with these plots, is that if you consider something that has a structure for the light ring that looks very, very similar from a black hole, and you can make that up, and if you consider an object that is sufficiently compact that you you have something like a light ring, and that can happen whenever it's sufficiently compact. Because the potential looks exactly the same in here, the initial parts, so this is an example where you have a point particle falling, in this case in a black hole, in this case in a wormhole, I know it's exotic, but just as an example. And the initial part of these two waveforms, they look exactly the same, essentially because this initial part is related to the light ring. It's not really related to having an horizon or not. You do start having some deviations if you wait long enough, because in a black hole, basically, you have your scattering potential related to the light ring, nothing else. And then the wave on this side just falls in and nothing else happens. Part of it goes back to you when you measure the ring down. But then your wave dies down over time. Now, in this example of a wormhole, you also have what I call trap modes related to the fact that besides the ring down, you also trap some modes in this cavity, and if you wait long enough, these modes will appear in your waveform at late times. This is actually a very generic effect if you consider generic beyond black hole objects that are sufficiently compact. Because the light ring is quite generic if you have an object that is sufficiently compact, but then what really regulates the late time response is related to having a surface or not. And so if you have a surface that reflects back your radiation, then you can have something that looks different from a black hole, but the initial part is not really related to, it's really only related to the photon sphere or light ring. Yeah. Okay, I'll finish here anyway.
Thank you very much, Richard. So I guess we reconvened on Wednesday for the Fundamental Physics part 2. I just wanted to emphasize again, please write your name and destination and train time on the blackboard or on the sheet in the entrance. And like dinner is at 7:30 as usual. Thank you again, Richard. Another round of applause for you.